Okay.
Can you talk? Can you talk?
Yeah, testing, testing.
Yeah. It's good.
Okay, we're good. Well, this is really your lucky morning because not only do you get to go through one of the most complicated problems in all of oceanography, but you get to go through it with me. So a double whammy against you here. Normally, Jeremy Wardell from NASA Goddard Space Flight Center gives this talk, but they still have him locked in a cage at Goddard, and he's actually driving somewhere at the moment. So he said he would try to listen in from his car, but that might or might not work. So anyway, this is basically Jeremy's talk with a few tweaks by me. And then of course, all the figures and everything come from a whole different group of people at NASA Goddard, all the ones that actually invented all of this stuff that we're going to talk about. Okay, so in the last lecture, I sort of introduced this atmospheric correction problem, which is given any of these spectra here, some way or another, you have to come up with this one for the water leaving radiance. And that's it. I just give you one of those and you're on your own. Okay, so what we're going to do today in this lecture is just work through the steps that the NASA Ocean Biology Processing Group goes through to actually do this. And, you know, we'll see what they're doing. We're not going to dig into all the math, of course, but anyway, you'll see how the process works. And along the way, we'll see places where ancillary data are required. That's things like maybe you need to know the ozone concentration or you need to know the sea level pressure or whatever. Well, that's not coming out of your MODIS or VIRS sensor. You have to get that some other way. And we'll see some places where they've built in assumed biooptical models that allow them to do part of the calculation. So that's where we're headed. Okay, the way the official documentation on all of this is this report here by me and Jeremy and a bunch of other people. And the way this report came about was about 5 or 6 of these classes ago. I'm sitting in the back of the room, Jeremy's giving this talk, and I'm sitting there thinking, you know, I just don't understand this stuff. It is such a complicated mess. And where did he get this equation? Where did he get that value? And then the next class, 2 years later, Jeremy's giving the talk. I'm sitting in the back of the room thinking, I really don't understand this stuff. So I ended up, you know, I asked him, like, is there some one document that just says, here's what we do? And the answer was no. There's like 30 different papers in the literature where this paper figured out how to correct for nitrogen dioxide. This paper figures out how to correct for ozone. And these 5 papers talk about how to correct for aerosols. And you had to go read all of these papers to understand the different pieces. So I actually sat down then and basically kind of interviewed all of these people with a whole bunch of phone conversations, because that was before the days of Zoom. And I wrote this big report that simply collects into one place. Here's what we're actually doing as of the date of the report. And then that became a chapter on the web book, and there's a whole chapter in the Ocean Optics book version. That is all the stuff that we're going to go through today. And this thing here is about 80 pages of equations and databases and such. So that's how this report came about, was simply from me not understanding what was going on in these lectures. Okay, so bottom line, you know, the sun's putting in sunlight here. Some of that gets into the water and some gets absorbed and some gets scattered and some makes it back out and finally gets back up to a satellite. So this whole lecture now is going to be talking about what's going on in the atmosphere here. And so you can just stop and think, you know, we saw this figure the other day of all these different things that can happen: Rayleigh scattering, aerosol scattering, and reflectance off the sea surface, and reflectance off of patches of foam from breaking waves, and on and on and on. So you just sort of sit down and say, well, what are all the things that can contribute to the top of the atmosphere radiance? So that's the LT, is the total radiance. That's at the top of the atmosphere. That's what my satellite measures. Well, you sit down, you scratch your head, and you say, well, there's Rayleigh scattering by atmospheric molecules. There's scattering off of aerosols. There's scattering off of aerosols that then scatters again by Rayleigh, or scatters off an atmospheric molecule and then scatters off an aerosol. And that's just called the aerosol-Rayleigh interaction. There's sun glint on the surface. There's background sky reflectance. There's reflectance from white caps. Oh, and then by the way, there is some water leaving radiance. So what we're going to have to do is figure out how to compute all of this stuff here, which is confusing us, and subtract that out of the total so that we're finally left with the water leaving radiance, which is what's telling us about what's going on in the ocean. And so there's a big problem here, and that's the processing constraints. So to put things in perspective, MODIS and VIIRS do about 14 orbits a day. And the distance between the day and the night, between sunrise and sunset, is more or less 20,000 kilometers. And MODIS looks at a scan angle of plus or minus 50 degrees off the nadir. It's about 1,200 pixels wide. And it's collecting about 24 million pixels per orbit of imagery. And VIIRS, it's about the same, except it has higher spatial resolution. It's about 2,500 pixels, and the alarm track resolution is 0.75 kilometers. MODIS is 1 kilometer. VIIRS is actually collecting 66 million pixels per orbit. That's just on the daylight side, of course. And then NASA guys say, well, we're only going to process this if the solar angle is less than 75 degrees. Okay, reasonable. And so that reduces things a bit. But then there's 2 MODIS sensors in orbit. There's 2 VIIRS in orbit at the moment. So you multiply all that together, they're collecting about 150 million pixels per orbit times 14 orbits a day. That's about 2.1 gigapixels per day. And every one of those pixels has to be atmospherically corrected. Well, so you went home last night, you thought about this problem, and you come up with this really clever way to do absolutely perfect atmospheric correction. And you'll get the water leaving radiance to 4 decimal places. So, and it only takes a second to do that, all those calculations. So you go down to Jeremy and say, Jeremy, I can do absolutely perfect atmospheric correction in 1 second per pixel. And he'll say, well, that's really nice and you're really smart, but we can't use it. So how come? Well, if you have to correct 2 billion pixels a day and each one takes a second, how long is that in more human scale terms? Anybody know how long 1 billion seconds is? I'm the only one here that's 2 billion seconds old. 2.1 billion pixels is 67 years at 1 second per pixel. So the bottom line is, just to break even, just to keep up with the day's collection, NASA has to process, for every day, they have to process about 34,000 pixels per second doing the atmospheric correction. 24 hours a day, 365 days a year. So every second of your time that I'm wasting here, Jeremy is back at Goddard doing atmospheric correction on 34,000 pixels. So you want this process to be as accurate as possible, but it absolutely has to be extremely fast. And so, and of course, there's more sensors coming down the road. There's 3 more VIIRS sensors scheduled, there's PACE, there's whatever else. So the load just gets bigger and bigger. So there's an enormous constraint on whatever you do for atmospheric correction. It just has to be extremely fast in computer time. Okay, so they take this equation where everything here is at the top of the atmosphere. The first thing they do is they say, well, let's take the sun glint term and we'll write that as a value at the surface and then some transmission that gets the surface value up to the top of the atmosphere. And they do the same thing for the white caps part. They rewrite it as something at the surface times a transmission that gets the white cap reflectance through the atmosphere and back to the top. And they do that for the water leaving radiance. So what they've done here is they have the capital T is what they call direct transmittance, and the little t is diffuse transmittance. Now the difference here is when I'm looking at the ocean and I see a little bit of sun glint off of a wave, that sun glint is coming just from one point on the ocean. I'm not seeing sun glint from over here. That's going off in that direction. So this direct transmittance is if you have something like sun glint or maybe a white cap where there's just one point that reflects into your sensor, they compute for the given sun angle, atmospheric conditions, etc. They compute this one path right here, and that's what they call the direct transmittance. And they're going to use that to get the sun glint from the surface up to my sensor. On the other hand, for something like water leaving radiance, it's coming out from all over the whole ocean and, you know, coming in from different directions and all getting up to me. And so there they have what's called the diffuse transmittance, where here's the water leaving radiance, and some of it goes this way, but some of it comes up over here and goes over here, and then gets scattered into my direction. Some from here, and so that gets scattered. And so they have a different function that takes something that's coming from the whole surface and getting it through to the top of the atmosphere. And that's what's called a diffuse transmittance. Okay, so they then take this equation and they rewrite it again. And they say, let's take all of these terms here and they rewrite them as here, for example, is the Rayleigh contribution at the top of the atmosphere. They take what they call a sort of standardized Rayleigh contribution, which is what the Rayleigh scattering would be if the sun were straight overhead, the viewing direction was straight down, and you had a standard atmosphere without all the aerosols and all of this stuff. But they compute the Rayleigh contribution for one sun angle, one viewing direction, one atmosphere. Then they factor out, this is diffuse transmittance by gases in the viewing direction, diffuse transmittance by atmospheric gases in the sun's direction, and then there's a polarization term here. So what they do is they say, okay, I'm going to do the calculation for this standardized Rayleigh thing once. Well, in the real world, the sun was over here and I was looking, you know, over here. I wasn't with the sun overhead and looking straight down. So they build up these lookup tables and they say, I'm going to take the sun's direction and I have to get the sunlight through the atmosphere coming along some slanted path, and then I'll compute this once and say, if the sun's here, this is how much light gets to the surface. And then for the viewing direction, if I'm looking in this direction as opposed to straight down, here's how much of that standard Rayleigh would actually make it to the top of the atmosphere. So they do all of these calculations once for a range of sun angles, atmospheric conditions, viewing directions, and of course it all depends on wavelength. And you build up all of these lookup tables once and for all, and you have this standard Rayleigh thing. So they take, to get the real Rayleigh for your sun angle, your viewing direction, etc., they take the standard Rayleigh and then they modify it using a lookup table for your particular sun angle, your particular viewing direction, your particular wavelength, etc. So the reason they rewrite that in this kind of way is so that they can do these calculations of all these transmittances and correction factors, do those once and build a big lookup table. And then all you have to do is say at this pixel, sun was here, I'm looking here, and the sea level pressure was this much, and boom, I go to the lookup table, I get a number, and I multiply it times the standard thing here, and now I get the Rayleigh contribution or the sun glint contribution or whatever it happens to be. So no calculations are done. They're just plugging into spots and lookup tables and getting pre-computed numbers. So that's all done to make things run as fast as possible.
In the last equation, 3.
Say again?
In equation 3, what is LWC?
White caps.
So that's the same as.
Yeah, I think that got called,
Okay.
here they were calling it F for foam, and here it got called WC for white caps, but same term. I should have caught that.
Okay, thank you.
Okay,
The lookup tables are just to get diffuse and direction.
yeah, we'll see a little bit more how it goes. Basically, there's a lookup table, and they're going to be functions of sun angle, viewing direction, azimuth relative to the sun, sometimes things like atmospheric pressure, humidity, etc.
Sorry. So even though the equation 2 only has the transmittance for LG, LF, and LW, it's these values are multiplied to every single component.
Yeah, so, well, we'll see how it works when we go on. But anyway, the theoreticians will, like a guy like me, will write this equation down and go contemplate these terms. But when they do the actual calculations, NASA is working with this equation and a whole bunch of pre-computed lookup tables. Okay, so let's carry on here. So I think I've maybe already said that. If we just consider the Rayleigh term here, it's written as a standard term times a bunch of diffuse transmittances. And so there's that term there. And so this little LR, the standard Rayleigh contribution, as I said, was computed with a standard atmosphere. They only use non-absorbing gases, which are nitrogen and oxygen. And then they use various sun and viewing geometries. And that's an enormous big calculation using atmospheric radiative transfer codes, including all the polarization and all of that. And it probably took like 3 months of supercomputer time to compute that little L sub little r. And then there's a polarization correction that depends on the atmosphere and surface polarization conditions, which is modeled once again. And then we have these diffuse transmittances, and this polarization factor is once again pre-computed and stored in lookup tables. And so then to evaluate the real Rayleigh contribution at the top of the atmosphere, they don't have to do any more radiative transfer calculations. They just look up numbers. Okay, so we're now going to go through these pieces one at a time, but keep in mind that what we want is the water leaving radiance, and then we're going to use that to compute a normalized remote sensing reflectance. And here he's kind of taken, he's kind of divided through by these factors here. And so we've got the water leaving radiance. We're going to normalize that to the extraterrestrial solar value. We're going to normalize it by the sun angle. We're going to put in all these diffuse transmittances, and the S here is an adjustment for the Earth-Sun distance. There's going to be a BRDF correction. There's going to be out-of-band corrections. All of this kind of stuff is going to get applied somewhere along the way, but all of those factors are pre-computed. Okay, so first of all, let's just look at the top of the atmosphere radiance. That's what we're measuring. Well, you've seen what these things look like. So here's top of the atmosphere, actually reflectance now, which is radiance times pi, basically, or RRS times pi. And, you know, here's some typical values. Notice they're very blue here. Well, that's because of Rayleigh scattering. And this is for particular sun angles, viewing directions, particular atmospheric models, and so forth. But here's the curves. And if you plot the, take these curves and plot the water leaving radiance values as a percentage of the top of the atmosphere contribution, well, you see in the red curve here, it's very high CDOM. That knocks down the water leaving radiance in the blue. And for this hot water with a high CDOM concentration, the water leaving radiance is only like 5% or so of the top of the atmosphere signal. For a more typical case one water open ocean, maybe it's 10%. If it's got a lot of sediment in the water, so it's highly scattering water. Well, it might even be 30 or 40% of the total, but the bottom line is it's generally 5 or 10%. So that means if the water leaving radiance is only 10% of the top of the atmosphere part, if we make a 0.5% error in atmospheric correction or an instrument calibration, that could make 10 times the error in the water leaving radiance. So it would be a 5% error in water leaving radiance if we make just a 0.5% error in the atmospheric correction. Okay, so here we're going to work through the flow chart of what they actually do. So we're starting out with the top of the atmosphere radiance. Here's a particular example, Gulf of Maine here at 443 nanometers, and that's in radiance units. So we're starting with this, and now first thing we're going to do is correct for gaseous absorption. So we know the viewing geometry, and so the direction of the sun, the direction of satellites looking, and so we can go off and get the right values out of these lookup tables for gaseous transmittance in direction of the viewing direction, gaseous transmittance from the sun's direction, and so forth. And so what do those transmittances look like? Well, here's ozone and water vapor transmittance as a function of, from 0, no light gets through, to 100 or to 1, the atmosphere is perfectly clear. And you see some blue here, which is oxygen absorption lines. You see some red, which is water vapor. But you can avoid those places where there's bad oxygen and water vapor effects simply by putting your bands where they're not affected by oxygen and water vapor absorption. So life is good. So that the gray bands there are the bands of some sensor. I don't remember if it's MODIS or what, but anyway, you can avoid these problems. But you look at ozone transmittance, that's rather broad band. And now it's extremely huge down below 320. And that's this whole business of the ozone layer protecting us from UV light. But there's actually also ozone absorption that's sort of in the green off to the red here. And, the transmittance is here for low ozone, maybe it filters out 2%. For really high ozone, maybe it filters out 6%, but it's broadband. So there's no way to avoid this ozone effect by simply, moving these bands around, because then you couldn't have any bands in the green and the areas that you're interested in. Same thing here. Here's nitrogen dioxide. It's a very broadband effect, more down in the UV and up to about the 550 or 600 nanometers. So there's no way to avoid the effects of nitrogen dioxide absorption. And here's just some atmospheric profiles of what those things look like. The ozone maxima tend to be up at like 10 or 20 or 30 kilometers. The nitrogen dioxide maxima, they're all right at the surface because that stuff comes out of smokestacks and car exhaust. Okay, so now let's talk about ozone, for example. You know what the spectral absorption by ozone looks like. It's basically this curve here, except this is plotted as a transmission instead of an absorption coefficient. But anyway, you know that. So it's just like a chlorophyll specific absorption. This is an ozone concentration specific absorption. And so we know that. Well, we now need to know how much ozone was there in this pixel. So there's the first place you need ancillary data. And there's a number of satellites that measure ozone. There's one of them called Ozone Mapping Instrument. And then there's been several, that's a rather old one, but it's sitting there sampling or measuring the ozone concentration. So if you're at this particular pixel right there, you have to go off and get the data from that satellite and say, what was the ozone concentration at that point right there? And then you know how to compute the ozone transmission. And that's now for a nadir viewing direction. So you're getting the ozone optical thickness. but your sensor, the sun was here and you were looking there. So you have to take the nadir viewing ozone thickness and you correct it for the sun angle and for the viewing direction. So if you're looking straight down and the sun's straight overhead, then the ozone transmission would be e to the minus ozone thickness. But the sunlight had to come in at a slanted angle, so there's a longer path for the ozone to absorb the light, and it had to get from the sea surface back to the satellite along a slanted path, so there's more opportunity for the ozone to absorb that light. So those 1/over cosine factors for the sun direction and the viewing direction are increasing the ozone absorption from its nadir value, and then you finally get a diffuse transmittance for ozone that you can now use to apply to do your ozone correction. And all of these other transmittances are handled the same sort of way. Yeah.
Tau is optical depth? Or?
Tau is an optical depth, so it's a non-dimensional optical depth. So this is absorption per Dobson unit or whatever it's measured in, or per number of molecules times the Dobson units or times the number of molecules gives you non-dimensional ozone optical depth. Okay, now of course you have to go get that ozone value. There's several different sensors that are out there for doing that. There's one called total ozone analysis from stratospheric and tropospheric components. There's ozone mapping system. There used to be a thing called TOMS, total ozone monitoring spectrometer. It's now been replaced by Earth probe total ozone monitoring spectrometer, and there's others. So you have to go to one of those places to get the ozone value, or if those guys are not up there running at the moment you need them, then you use climatology. But of course, the different instruments here, there's three of them. Three of them here, the red, the green, and the blue. The blue is climatology, so it's the same from one year to the next. But the other instruments often give you considerably different values. And that's just another source of error when you go to do your atmospheric correction as to which instrument you're using. Yeah, Anna.
Which one does NASA use?
Well, which one they use is their preferred one, I don't know. They're all out there, and I think they probably have one they try to use, and if it's not available that day, they grab another one. But if Jeremy were online, he could answer that. Okay, here's what dioxide looks like. We saw an ozone map. This is that. Here's the East Coast. Notice very high nitrogen dioxide concentrations around New York City and Philadelphia. Nothing out in the open ocean. That's just all the people driving around and all the coal-fired power plants and all of that. So if you're out here, you're not going to have any problem with nitrogen dioxide. If you want to do remote sensing just off the coast of New York City, you have a big nitrogen dioxide correction to make. Or if you're downwind from the coast of China, for example, you're going to get whatever they're putting into the air there. Okay, that's just to show you kind of what it looks like. So we, and here's now this TG, that's the diffuse transmittance for gases in the sensor viewing direction at 443. And you can see the numbers are like 0.99 up to 1. So the atmosphere is very transparent, but still here this kind of yucky brown color, that's, you know, a 0.996 transmittance, which sounds like almost 1, but still it becomes important if you're trying to get 0.5% accuracy on your atmospheric corrections. And here's the gaseous transmittance in the sun's direction. In this case, it's pretty uniform, except right there by New York City or Boston. And those numbers are kind of 0.995, it looks like. So 0.5% is being lost due to the absorption by atmospheric gases. Anyway, we now have sort of computed some of these terms. We've done the, let's see, F there was the foam term, and we know these terms now there's a polarization correction. Some of the instruments are insensitive to polarization, like CWIFS was, but MODIS, for example, has a polarization dependency. So there's an extra correction that is done to the MODIS instruments to account for polarization effects. And of course, you know what instrument you're correcting. You've pre-computed what this is for a given sun angle, given viewing direction, and so forth. So they know from the pre-launch measurements what the polarization sensitivity of the instrument is. Okay, so we're down now. We're correcting for polarization, and here's this FP term, polarization at 443. Here's some correction here. And so this thing is going to get applied. And this all goes back to calculations by Howard Gordon and other people as to how they computed all of those lookup tables. And so now we've taken care of this polarization term, and that's getting applied to all of this stuff. And then how about foam and whitecaps? Well, here's some data that shows, as a function of wind speed, the fraction of the water surface that's covered by whitecaps. So below about 5 meters per second wind speed, you don't really have any whitecaps. If you're up at 10 meters per second wind speed, then something like maybe 15 or 20% of the surface, of the sea surface, actually has foam on it, or in either from a wave that just broke or a wave that broke 5 seconds ago. Well, of course, the foam is much more reflective than the dark water. So there's a little formula here based on data like this that says that if I have a given wind speed, I can predict the reflectance of the water surface for that wind speed. And here's the fraction of the surface that's covered by whitecaps. Here's that curve. There's another little factor here that they take to be 0.22. That's a correction for decreasing reflectance in the red and IR, or that's added in. So anyway, they have a little function here that basically all you have to do is plug in the wind speed and you get back the reflectance of the whitecap. And so then they can use that to figure out for the wind speed they have, how much of a correction for whitecaps do they need to do? Well, where do they get the wind speed? Well, that has to come from some other satellite or from a weather forecast model. So you have these global forecast models and you look and you say, well, this pixel, it says the wind speed 6 meters per second. So I know what number to plug in here and get the reflectance of the whitecaps that I can then use to correct for the foam contribution. Okay, so here's wind speeds here. And you know, it's really blowing out here. It's not much here. Here's this diffuse transmittance for the foam term at 443 nanometers. Well, it looks like there's not much of a correction down here, and there's a big correction out here where the wind is blowing. Okay, so they apply that. And now we've somewhere along here taken care of correcting for the foam or whitecap contribution. So now they go, next thing is to look at the Rayleigh contribution. Okay, we've sort of said this, you know what Rayleigh scattering is, and it's very strongly correcting or very strongly contributing at the blue wavelengths, but the phase function is equal forward and backward scattering. Okay, so we've seen this before. They've pre-computed this guy. They have lookup tables for these gaseous diffuse transmittances as a function of viewing direction, sun angle. They've got a polarization correction that they may have to apply. So all of these things here are known. And, you know, I said they developed one lookup table for this LR computed with a standard atmosphere of non-absorbing gases in various sun and viewing geometries. And so they just go look up the tables and they come up with the Rayleigh contribution. And it actually includes the reflectance part of the background sky is built into the Rayleigh tables. Okay, without doing all of this stuff, you would have to run an atmospheric radiative transfer model, which would take you all day. Yeah, Ben.
So this is just multiply 4 numbers.
Yeah, just 4 numbers. You like I say, you know the sun direction, you know the viewing direction, you know the wavelength, you know whatever else it was, which instrument it is. So you just go to these big lookup tables. You get the number for TGV, the number for TGS, the number for FP, the number for the standard Rayleigh thing. You multiply 4 numbers together, and that's your Rayleigh contribution. And it may not be perfect, but it's fast. Okay, so here's just more info about the Rayleigh stuff. So this is the atmospheric pressure at a given moment, July, well, actually, it looks like a weekly average, July 2002. Now, what you do in that previous calculation here, this standard Rayleigh thing is for the average atmospheric pressure, 13.25 millibars. So that's done once. But if it's the pixel you're looking at has high atmospheric pressure, that means there's actually more molecules between the sea surface and the satellite. Or if it's a low pressure area, there's a few less molecules of air between the sea surface and the atmosphere. So they actually take the numbers that they're getting out of the lookup table business and they say, well, let's correct that a little bit for the atmospheric pressure at our particular pixel versus the standard atmospheric pressure. So that could be a few percent correction. And then you get a little bit better Rayleigh aerosol or Rayleigh optical thickness. And so then to get this atmospheric pressure, well, they have to go over and look at a weather map and they come up with that. Or there are satellites that measure things like surface wind speed and atmospheric pressure. So somewhere or another, that's another bit of ancillary data, but they get a little bit better value there to use to do the Rayleigh correction. And here's a plot here of the top of the atmosphere reflectance and then the reflected ratio value. And you see the ratio, it's a little hard here. This is the ratio, this red curve of Rayleigh to total. So out at towards 900 nanometers, the ratio is about half. But up at the blue wavelengths at 400, the Rayleigh is basically 80 or 90% of the top of the atmosphere contribution. So it's a really important correction to make. In general, 50 to 90% is Rayleigh for what you're measuring at the top of the atmosphere. Fortunately, that's a fairly easy correction to make. Okay, so we've now we're now have figured out the Rayleigh contribution. So we're going to take the top of the atmosphere value minus, this is the Rayleigh term here, and that gives us what's left over. And these are all on the same scale. So they just expanded the scale here and you see a little bit better now what we're left with after we've now done the gas absorption, the polarization, the foam, and then finally the Rayleigh correction. We've now gone from this to this. Okay, what's coming up next? Remove the glint. Okay, that's this term here. We've now fixed up the Rayleigh term. So, of course, if you have a lot of sun glint, all you're seeing is light reflected off the surface. You can't see what's going on with the water leaving radiance. Okay, so that's just a couple of pictures. There's glint at the beach, but here's what it looks like in a satellite image. You're obviously seeing something going on here, which is sun glint. You know, the sun's up here, it's reflecting off the surface and coming back to you. And out here, you're seeing dark water because it's not contaminated by glint. Okay, here's a couple more simulations. Some of these instruments can, as they're flying along, if the time of day has the sun over here, then they can tilt a little bit and look away from the sun and avoid the glint. And other instruments, CWIFs could do that, for example. MODIS can't. So MODIS just flies along and it does its swath, and you may or may not get glint. So there's simulations here here's the swath the satellite's seeing in white. And if you had a 20-degree tilt for some particular conditions, you have this little spot here that's going to be contaminated by glint. If you are looking straight down, then you have a bigger spot here that's knocked out by sun glint. So these guys do, when you're designing satellite orbits and such, they do enormous amounts of calculation to figure out what kind of orbit they want to have, when do they want to have it fly over, and all of that. And a large part of that is to figure out how to minimize the pixels that are simply unusable because of sun glint. But you'll still have, even though this is sort of the really bright areas you just can't use, you'll still have some glint outside that, and you may be able to correct for that. Yeah.
What's the dark band going across the C-West one? Kind of, yeah,
That's the area that's no good because there's just too much glint to handle.
the horizontal, like.
Oh, this right there? I don't know what that is. I hadn't even noticed
I
it.
think that's the period that's tilting.
It's what?
It's the period that's tilting. It takes
Oh, okay.
as it goes over.
Okay, so that's missing data then,
And
basically.
one other thing to mention is that it's not like MODIS, when it was designed, they weren't as smart as CWIS and thought, oh, okay, I'll go without tilt because I don't care. It's because CWIS is a dedicated ocean color satellite. So it did tilt. MODIS was atmospheres, oceans, and land. And the land guys don't, a lot of the communities don't want us to tilt. So that's why that.
Yeah. There's always reasons for things. Okay. So on the sun glint business, then they write the sun glint term. So this is at the surface transmitted through, that they actually rewrite that in terms of a normalized glint. And then that gets multiplied by the extraterrestrial solar irradiance to set the magnitude. There's an atmospheric transmission to get the light down, another transmission to get the light back up through the atmosphere. And then they go off to these normalized glints, which are for various wind speeds. And, you know, this is for one sun angle, one azimuthal angle, et cetera, and then different wind speeds. So they compute what this normalized glint would look like as a function of wind speed and in whatever the geometry is. And then they take that number and they dig into the lookup tables and get these other numbers. And then they come up eventually with a glint calculation. And so here, the catch though is that these transmittances depend on both Rayleigh and aerosol contributions, then corrected by sun angles. And at the moment, we don't know what the aerosol part is here. So they actually do a little iteration here where they say, okay, let's start out. We have the total at the top. We have the wind speed. We'll make a guess at the atmosphere, at the aerosol transmission. And they use an initial guess of 0.1 for that aerosol transmission. And then they come up with a little second guess here as to how much the glint contribution would be. And then they iterate through that a couple of times and see if they get a stable result. And enough said on that, you know, all the details are in those reports, but basically they, in order to get this term here, they need to know both the Rayleigh, which we now know, but the aerosol optical thickness in order to get these transmissions to correct for the glint. And so they just do this little iteration thing, get a couple of better guesses at the aerosol optical thickness, and then they use that to actually do the glint correction. And it might not be perfect, but it's fast. Okay, so here we've now, here's a map of wind speed. So it's windy here, it's windy here, it's not too bad here. And then here's the corresponding term That's this glint correction. And notice there's basically no correction being done here. There's a big correction here where there's a lot of, where the wind is high. So you're getting a lot of glint, but the wind is high over here too, but there's no glint correction. Well, that's because for this geometry of this figure, you're seeing this glint. Like I'm looking down here and the sun was over here somewhere. So I was seeing the glint, but the glint that was over here, it's going off in some other direction. It's not affecting my pixel. So there was no glint correction, even though the wind was high. So anyway, they've now take these kind of numbers here. And if this LGN, if it's less than a small number, they remove the glint. If this wind speed and all this other stuff is too big, they just say, we can't correct for this, just flag the pixel as unusable. And so it gets a high glint flag, and that's nature's way of telling you, don't trust this pixel. Okay, so yeah, Anna.
For sensors that tilt, you don't have to do these calculations, we can assume.
Well, so NASA's doing this, and what they do is they look and they say, okay, here there's a pretty small glint correction. So if we go back to this thing, this is this LGN, and here's this cutoff at 0.005, and this is kind of a non-dimensional measure of glint. If the wind speed and the viewing direction are such that the glint, normalized glint, is less than this value, then they say we can go ahead and correct for this. If there's so much glint that it's bigger than this 0.005, they just say it's hopeless, flag the pixel as contaminated by glint. It's just too big for us to correct.
But do they do this when the sensor is tilting?
Yeah, it's done to every pixel, but they decide pixel by pixel whether there's hope to correct for the glint or not.
Jeremy, who's playing against Ozone, he knows ours works too.
Okay.
So it's a little bit slow. He says it's a use correction for every.
But my understanding is they do it, but they some way flag the pixel as high glint. Now maybe today they're doing it for all of them.
They're doing it for every.
Okay.
Yes.
Okay, so that's a little change from when the report was written then.
They do every pixel, I think. It's just that, and they do the correction every pixel, but they flag. There's a whole series of flags when you get the data associated with each pixel. They set one of the flags as the glint flag, and they set that as a high glint. So when you're using data, you take, if you don't want those in there, you make sure that you don't collect data that has that flag.
Yeah, Ben.
Just a question, is base going to tilt to correct the glint, or is it just going to fly straight?
I defer that to Emmanuel or somebody who's on the PACE thing. So the next correction is PACE going to tilt, or is it like MODIS?
I think it's going to tilt. Yes, it will.
Okay, PACE will tilt then. Okay, so now we've applied all of this stuff. We removed the glint, and we've taken care of wherever it was, this term here. Now we get to the hard part, which is the aerosol business. Okay, so they've built an enormous number of lookup tables for different aerosol properties. And the aerosols are characterized by their particle size distribution, their complex index of refraction, the real and imaginary parts. And then they've done a lot of calculations with me theory, where you take the particle size distribution, you assume the particles are spherical. They come up with a phase function, single scattering albedo, and extinction coefficient, or beam C, for a particular aerosol. And then you can compute the aerosol optical depth or optical thickness by integrating the beam attenuation coefficient from the surface to the top of the atmosphere. Now, how they come up with these phase functions and so forth, well, here's some typical aerosol particle size distributions This one is for typical coastal or urban aerosols, and this one is for typical open ocean or maritime aerosols. You'll notice the urban aerosols, that tends to be either dust blowing off the land or soot particles out of a power plant, something like that. There's relatively more small particles than big ones, and they call them actually fine and coarse particles in the particle size distribution world. With the open ocean aerosols, that tends to be more big sea salt particles. So you have relatively more large particles than you do small ones, and those are larger sea salt particles. Now, these three curves here, same particle type, but different relative humidities, 50%, 80%, and 95%. Because these aerosol particles, they absorb the water from the atmosphere, and they swell up a little bit. So that changes their size distribution. So the high relative humidity particles tend to be bigger than the same particle in low relative humidity. So they've built up tables where they use 10 different particle size distributions and 8 different relative humidities. And then for a given particle size distribution, a given relative humidity, one of these curves here, and the index refraction of the sea salt particle or the soot particle or the dust particle, then you can go off and compute the corresponding phase function, which you're then going to use in your radiative transfer calculations to build these big lookup tables. Then they come along, well, actually, here's some more info on that. So the aerosol optical thickness is a function of wavelength relative to the value at some reference wavelength tends to be a wavelength, 1/wavelength to an alpha, and this alpha is generally called the angstrom exponent. And that alpha then depends on the relative humidity and all of that stuff. So here's values of aerosol reflectances for different aerosols. These are different size ranges and different, 3 different size ranges. And here's one nadir viewing direction, sun at 42 degrees, an optical thickness of 0.086 and so forth. So you get some different curves here for the different aerosol types. Now, what they're going to do in just a minute is we're going to use the ratio of the aerosol absorption at, in this case, 748 to 869 nanometers and come up with this function epsilon, which we're going to see in just a minute. And these values are going to come from the wavelength bands that are in the near IR. Okay, so we're still working on this. We still don't quite know what we're going to do here, but if we go to here, what we're going to do is the following, and this is the real crux of the matter. They've computed this epsilon function, which is a ratio. Remember, that's the ratio of the wavelength here, in this case, epsilon 748 to 869, but we're just going to use any wavelength here to 869. So they do all this B calculation stuff. They come up with a table of these epsilon values. So here's what they look like. So here's the table for one sun angle, 30 degrees, one viewing direction, one azimuthal angle between the sun and the viewing direction, one relative humidity, and then here's some different, these are the different aerosol types. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I said a minute ago that they, wherever it went, they have 10 particle size distributions and 8 relative humidities. So here's for 10 different particle size distributions, which have a sort of effective size from 0.17 micrometers up to about 2.8 micrometers. So these are the values of this epsilon lambda relative to 865 for 10 different aerosol types, and this plot is for one relative humidity. So there's 8 more plots like this for the other 8 relative humidities. So here's the deal. You come along here, your satellite observes this 865 band, and it observes the 765 or whatever it was. So you have these two values right there. And we're going to use those values to figure out which of these curves we're going to use for the aerosol correction. So what we're assuming here is that at these wavelengths, all of the top of the atmosphere radiance is coming from the atmosphere. There's no water leaving radiance beyond 700 something, and that's the so-called black pixel approximation. So water absorption is going way up beyond 700, and we're going to assume that everything we measure at the top of the atmosphere at these two wavelengths is coming from the atmosphere. We've subtracted out all this Rayleigh and everything else, and so we're going to assume that what's left is all from aerosols, aerosol scattering. So how good is that black pixel assumption? Well, here's data from the Sargasso Sea, and we're going to be looking out here at 860 and 7, whatever it was here. There's basically no water leaving radiance, so that works just fine. Here's Chesapeake Bay. Now we're going to be looking out here at 860 and 7, whatever. Now there's a significant amount of water leaving radiance. So that black pixel assumption is no good, and therefore you cannot assume that the top of the atmosphere radiance was coming entirely from aerosols, because part of it, at least at this wavelength, is actually water leaving radiance. So that opens a whole nother can of worms. Here's a little blow up of that. And it doesn't look like much, but it's very significant when you're trying to get a 0.5% accuracy on your atmospheric correction. So let's suppose that you just assume that the water leaving radiance is 0. You go through this, you do your calculations, and if you happen to be in Chesapeake Bay, I think this was, here's what happens. Here's the remote sensing reflectance at 412. The little dashed line is 0. You're getting a lot of negative water leaving radiances or negative reflectances. Well, you get chlorophylls that are much too small here. The gray is the retrieved chlorophyll. Oh, no, sorry, the blue is the retrieved chlorophyll, and the gray is the actual measured distribution. So your chlorophylls are off. And here, if you look at a time series of, this is remote sensing reflectance at 412, notice how many of them are negative. So you just know something's wrong. And then here's the chlorophylls, the measured values are the dots, the retrieved are the blue, and you can see the measured values are way less than the retrieved values. So yeah, this is lower Chesapeake Bay. So by not accounting for the fact that there was non-zero water leaving radiance, you've really gotten a bad retrieval here. Okay, so what do you do then when you figure that there's, your black pixel assumption is not good? Well, there's a lot of ways people have cooked up to try to handle that problem. And so there's several papers here that I've cited. They can use, like, for example, you can go further out into the infrared if your sensor has those wavelengths, and then you're pretty sure it's 0 water leaving radiance. There's other schemes people have cooked up. There's various schemes where you do a couple ocean atmosphere matching thing and sort of iterate. Those can all be very computationally expensive, even though they work. So what I'm going to talk about today is what NASA is doing at the moment, which is in this paper by Sean Bailey. And notice also here, every once in a while, every few years, NASA comes up with better algorithms for doing whatever. And so they, test those ad nauseum. Those new algorithms will finally get the blessing of everybody. And they will then become the algorithms that's used for some particular correction going forward. And then they back up and they reprocess all of the historical data using the new algorithms. So that's just a phenomenal amount of computer time. But they will, like, they did a reprocessing in 2000 where they used a new algorithm for this black pixel thing. Then somebody else came up with a better way to do it. So they did the reprocessing again. And then they come up with a little better way. So they did the reprocessing again. And so you can go back and look at this historical data and know that even though it was CWIFs, that it's getting the current set of algorithms applied to that data, just like the current MODIS or VIIRS data. So it's an astounding amount of work that NASA does down there. Okay, so what NASA does at the moment, and this is just like it's a mess, but this is out of the report. So they come along and they start out and then they say, assume that RRS at 765 and 865 are both zero. So they're going to start out and say, make the black pixel assumption. They go through, they do the atmospheric correction process that you just worked our way through. And then they get RRS at 443 and 555 from this initial atmospheric correction, making the black pixel assumption. And they get a function here, eta, that uses those first round of values for RRS. Then they use that to get an initial estimate of the chlorophyll concentration. Now, this is a little biooptical model here that's based on playing around with a lot of data. So they take their RRSs, basically a band ratio algorithm, they get this function, they eventually come up with a guess for the chlorophyll. Then they use that chlorophyll to try to get absorption at 670 by another biooptical model where they plug in the chlorophyll here and they know the absorption for water. Then they take those values and they stick them back into this other equation up here, and they try to get a scattering coefficient at 670. And then they get a backscatter coefficient. And then they do another calculation here using those scattering and absorption coefficients, assuming that it was case one water, because that's where this biooptical model comes from. So they go through all of that. Then they come along and they take these values at 670 and they use the wavelength dependent biooptical model, and they try to come up with a scattering coefficient of 765. And then they can use that to try to get the new value for what was actually leaving the water at 765. So that's now a non-zero RRS, or non-zero water leaving radiance at 765. And then they use that to remove the atmospheric contribution. And then they do the same thing at 865, because that might have been non-zero as well. And then you go back to the top and you do the whole thing over. And instead of starting out by assuming back here that the water leaving radiance was zero, you've now gone through this calculation and you have a better guess that the water leaving radiance wasn't really zero, it was these values. So you repeat the whole process and you iterate 2 or 3 times here. And then they do this until the change from one iteration to the next is less than 2%. And that's usually 2 or 3 or 4 iterations, or just give up after 10 iterations. So that's a way of trying to get some guess as to how much the water leaving radiance was at those 2 IR wavelengths. And yeah, it's a mess. I don't go around with this stuff in my head, believe me. Okay, so they eventually do this, and it says that they don't do this whole business if their first guess chlorophyll is less than 0.3 milligrams per cubic meter, because that's pretty clear water. You must be in the open ocean. There's probably your black pixel assumption is good. They always do it if chlorophyll is greater than 0.3. Let's see. I think that should be 3, not 0.3. Then they, in between 0.3 and 3, they will do the correction, and they'll do both the black and the non-black pixel assumption and interpolate in between. And the different sensors, of course, have slightly different wavelengths bands that they use for these two near IR bands. So there's just what those are. Okay, so here's the gray area here is where chlorophyll is less than 0.03, the white where it's on average more than 0.03. So they don't do the assumption, or don't do the black pixel calculation when chlorophyll is less than 0.03, and here it says 0.07, they always do it. That's was a typo on that previous slide. And then they interpolate between them in between here. Okay, so then if you do the black pixel thing applied to this image in the lower Chesapeake Bay, now you notice your RRSs are almost all positive like they should be. The chlorophyll retrievals are matching much closer to the measure. Here's RRSs that are now all positive. Here's your retrieved chlorophylls. They're looking as good as you'll ever do. So this does work pretty well. And this is what they're doing from 2000 to the present. And of course, if Emmanuel were in the back of the room, he would be saying, well, you should read this paper. The Maris people do it this way, and the Koreans do it this way, and the Indians this way, and the Chinese do something else. Well, that's all true, but this is what NASA does. So, and I comment here, a little political thing. NASA puts all of this stuff out there. It's not even that they'll show you the equations. You can go in and download all these databases and play around with them all you want. And I remember talking to Paula Bontempi, ex-student of this class, and longtime program manager at NASA. And she said she was having these conversations with a different country one time, trying to work out arrangements between NASA and this country. And NASA's, got all this stuff online. You can go in and pick it apart. And the negotiator guy for the other country said, if somebody finds a mistake in one of those algorithms, you're going to look really bad. And that's such a different viewpoint. NASA's saying, here it is, take a look at it. If you can find a bug and fix it, great. And the other viewpoint was, if you've got a bug in this program or your algorithm, you're going to look bad if somebody finds that bug. So got to cover it up. It's a much different view of things. And, with Hydrolite, you get the source code. And if you can go into insides of Hydrolite down deep in the math and fix a bug for me for free, I'm super happy. And I've had people that dig around inside and like improve the little numerical algorithm so it runs a little bit faster. Man, that's great. So science should be open. And, a lot of countries will not show you how they do atmospheric correction. And therefore, you can get their imagery, but you don't really know how much to trust it because you're not sure what they really did. And NASA is completely above board. Here it is. Take a look. And that's really commendable. Okay. Enough said there. So, yeah, there are other selection schemes. There's one called multiband atmospheric correction, which uses several wavelengths out in the near IR, not just two. And there's a Gordon and Wang paper from '94. There's also some assumptions in there about single scattering versus multiple and all of that. And this, my understanding, is going to be used with PACE because it has these extra wavelengths out there. There's another scheme here that's a spectrum matching approach that is getting used more in Europe these days. So there's the Maris people using that. There's a bunch of fancier radiative transfer coupled ocean atmosphere things. They work nice, but they're computationally expensive. So there are other techniques for handling non-black pixel waters, but with NASA, it's all about speed because of all the instruments they have. So here's now the next problem is absorbing aerosols. So all of these databases are built on the assumption that the aerosols are non-absorbing. So that's a good assumption for sea salt aerosols, for example. Well, what happens is you make these two measurements out here, and let's say it picks this green aerosol right here, which is built on the assumption that the aerosol is non-absorbing. Well, what happens with absorbing aerosols is they tend to be highly absorbing at blue wavelengths. So an absorbing aerosol may look exactly the same back here, but then you get into the blue, this curve drops down like this. So what happens is you've got your radiances here from the instrument, you've done all this other previous correction, and now you say, what value do I need to subtract out at, let's say, 400 nanometers to do the aerosol correction? So you go back, you look at these things, maybe you do the black pixel thing, maybe you correct for that. But anyway, it comes back and says, these 2 points back here have picked this aerosol contribution. So at 400, I need to subtract out this value. And you subtract it out, and you're subtracting too much because for absorbing aerosol, you should have subtracted this value. So you take what's left, you subtract this, and you get a negative radiance or a negative reflectance because you actually had an absorbing aerosol and you didn't know it. So then the question is, well, how do we find that whether it's an absorbing aerosol or not? So, for example, if we use the wavelength, so let's say back here, maybe at 350, it would have no problem telling the difference between the non-absorbing and the absorbing aerosols. So why don't we just use a wavelength? We'll use these two wavelengths, but we'll add one back at 350, and then we can spot whether it's an absorbing aerosol or not. So why don't they do that?
You already put the answer.
Because what?
You already put the answer.
Well, no. Why can't I use a wavelength back at 350 or 400 and do the same thing I did out here?
Rayleigh scattering? Rayleigh scattering.
No, we can correct for Rayleigh quite well. It's almost too easy. It's because back here, you can never assume that the water leaving radiance is zero. You just know it's going to be some big number because of whatever's going on in the ocean. So here, we're trying to assume that the water leaving radiance is zero, or if it's not, we can do a little bit of a correction. Back here, we just know there's going to be some big non-zero water leaving radiance. And so we just can't use those bands to flag whether it's an absorbing or non-absorbing aerosol. Okay, whoops. So yeah, there's the answer. The water's not black back here. Okay, so then the question is, well, if we go down to, let's say, 300 nanometers or 250 or something, there, the absorption by even a tiny little bit of UV in the water will give you an enormously high absorption. And so then also if like water absorption starts going back up in the UV. So if you went down to say 250 nanometers, you can be guaranteed that there's no water leaving radiance. The black pixel assumption is perfectly good. So why not put a band at 250 or 280 or something like that? And then we can make the black pixel assumption and we could spot the difference in the non-absorbing aerosol and the absorbing aerosol. So why don't they do a band down somewhere below 300 nanometers?
Because ozone sucks it all up.
Because what?
Ozone absorbs everything.
Well, ozone does absorb very strongly down there, so that's one reason. But it's, nobody does remote sensing below 300 nanometers. Well, that could be, but the real answer is there ain't no sunlight down there. So here's the top curve here is the extraterrestrial solar irradiance, and it is, say 300 nanometers, it's about 0.5 watts per square meter per nanometer. But by the time you get that light through the atmosphere, and in particular through the ozone layer, there's essentially no sunlight reaching the surface below 300 nanometers. So it's just basically absolutely dark. You just can't get through the ozone layer. So that's why you can't put a band down here and some way you look at the sea surface is the ozone. It just makes the atmosphere completely opaque. And so if you went outside with an instrument that measures, you know, downwelling irradiance at 250 nanometers, it's going to give you 0 on any average day. Okay, so we're kind of stuck with this. And I remember when I was going through and interviewing Wardell and Company, and I get through all this, and I said, well, then what do you guys do when there's an absorbing aerosol? And the answer is nothing. There's nothing we can do. We just have to assume the aerosols are non-absorbing because we have no way of pegging that it was actually an absorbing aerosol. And so all you can do is do the corrections for non-absorbing aerosols, hope for the best, and then you look at your data and find out you have a bunch of negative reflectances down in the blue. That's kind of nature's way of telling you that you really had absorbing aerosols. Then, if you want, you can go back to NASA and get that level 1B or 1A, whatever it is, top of the atmosphere stuff, and do your own atmospheric correction and say, I know I have absorbing aerosols here. I know they're soot particles. I'm going to come up now with this black curve here, and I'll use that to do my own atmospheric correction. And then away you go. So, but for the routine processing, there's no way that they can tell the green curve from the black curve there. So they just go with the green curve and hope for the best. And of course, you can figure if you're downwind from New York City or China or wherever, you probably have absorbing aerosols. So be aware that your data, your retrievals may or may not be good. Okay, so where are we here? We've now removed aerosols. So we start with what we had before. There's the aerosol correction at 443 or the aerosol radiance. And we take this minus this, and now we have a water leaving radiance at 443. And so we've removed the aerosols. And now we have to say, this is still for particular sun angle viewing direction. So we now try to do this business of normalizing things to where the sun is straight overhead, the viewing direction is straight down. And so that's what then comes up next. We've now checked off the aerosol part. We still have this BRDF correction and the out of band correction. So what they do next then is this, Kim talked a little bit about the spectral out of band business. So here's the modus aqua bands, actual sensor responses at the different bands. And, you know, you look at that and say, hey, this is great. You know, this band, this one, this one, this one, they had a little bit of overlap there, but whatever. And so they look really good on a linear plot. But if you plot that stuff on a log scale, now if you pick this red band here, for example, at 760 or whatever it is, well, here's that red band, and it sort of spreads out all the way down to 400, and it's sensitive all the way out to 1,000. So what you think you're measuring at this band here is actually picking up light from down here and out here. And that's the out of band response business. And, you know, you notice the out of band values, they're down like 3 or 4 orders of magnitude from the peak, but still that matters when you're trying to be as accurate as possible. So this stuff you measure in the lab for your instrument before the instrument is launched, so you know what these curves look like. And then you have to come along here and do a correction for the fact that if you were looking at the red band and you had this measurement back in the blue, you know, you're picking up a little bit of this blue light and you're picking up a certain amount of whatever's out here. And then you can correct the central band here for that out of band response. Okay, the other thing that happens is, and of course, this out of band business, that's different for every band and every sensor. So different lookup tables. Here's the satellite, what it's really seeing. Here's your in situ filter. So this is on your radiometer that you're going out and getting, ground truth with. And you kind of have to realize that what the satellite is seeing is not, even though it's called, let's say, 440 to 450 nanometers, it's not really just that, but your instrument may be doing a much better job of just collecting light from 440 to 450. So once again, there's a bunch of little corrections that you have to apply, which may not look too big, but they're a few percent. They depend on chlorophyll concentration. And here they could be, looks like 9% at low chlorophyll and up to 1.01 factor at high chlorophyll. So all of these little things, if you're really trying to do extremely accurate comparisons between ground truth and satellite stuff, all of this has to get worried about. And so then we've now done this bandpass correction business, and somewhere here, yeah, we've now done the bandpass. Now we have to do the BRDF correction. And so the idea here is during the day, the sun's here, and you make an in situ measurement. And here's the chlorophyll in the water. You get your values. Well, the day goes on, and pretty soon, 3 or 4 hours later, the satellite comes over, and you get its value, and you get its retrieved chlorophyll. But of course, the ocean may have changed in that 3 or 4 hours. The chlorophyll's increased a little bit, or it's gone deeper, or whatever. So then we have to correct for this so-called bidirectional reflectance business. Once again, big lookup tables. So Morel, what he did was he did a bunch of hydrolyte runs and atmospheric runs for different path lengths through the atmosphere, different transmission of light through the air-sea interface. That means different wind speeds and waves on the surface, different volume scattering functions as a function of chlorophyll. And he comes up with these big lookup tables here, which are a function of wind speed. So this ratio here does the correction for surface reflectance between your viewing direction versus looking straight down for the given wind speed. This F over Q business depends on which atmosphere you're using, what the wind speed is, and what the water IOPs are. And the water IOPs depend on the chlorophyll concentration. So basically, you kind of go through, you do a retrieval, you come up with a first guess for the chlorophyll concentration. Then you go back and you plug that in here in your lookup table, and you got this big shaded factor here, and you apply that and you get a new water leaving radiance. You do a new chlorophyll retrieval with new water leaving radiance. And then you can come up and apply this again. So there's a little bit of correction done there. But notice these lookup tables, they were created using hydrolyte as a function of chlorophyll for case 1 water only. So they work great in the open ocean where it's case 1 water. They might not work so well in Chesapeake Bay or the Gulf of Maine where it's not case 2 or case 1 water, but you're kind of on your own there. And other people since have now developed these kind of lookup tables for various case 2 waters. And I think the Europeans tend to use those, but this is what NASA's still doing. And, the Europeans, in many cases, they're interested in the coastal waters around Europe, whereas NASA's processing the whole world. Okay, so anyway, this is just another big lookup table that will take your water leaving radiance from its particular viewing direction and turn it into this normalized guy. And then you finally get this normalized, what Morel calls the exact normalized water leaving reflectance. And that's what you finally then do your final retrievals with. And these factors here, this F over Q business, here's just a table of, as a function of chlorophyll, those values tend to be anywhere from like 0.6 up to, you know, about 1. So they're pretty big correction factors, or can be. And this is for different viewing directions or sun angles. I don't remember which it was. And different wavelengths are all in here. So basically just a big lookup table. And I think you saw this the other day. How much difference does all of this make? Well, at very low chlorophylls, the BRDF correction is not too big. At higher chlorophylls, it then becomes significant. So the dashed lines here are the uncorrected. The solid lines are after doing the BRDF correction. Okay, that's it. So then here's the BRDF correction values for that image. And, you know, there are factors of typical 0.95. So that's a correction factor that gets applied to do the BRDF correction. And then finally, you now have the retrieved water leaving radiance from which you get your normalized exact water leaving reflectance. And you now go plug that in to your favorite retrieval model to get chlorophyll or absorption or CDOM concentration or whatever it is. And you wish it were perfect, but you know it really isn't. But it's astounding that they can go through all of this at 35,000 pixels a second. Okay, we've mentioned that you have ancillary data requirements. You need to get atmospheric pressure, that's for the Rayleigh correction. Water vapor, that helps you pick the aerosols, relative humidity, wind speed. You need the ozone, you need the NO2 concentration. INCEP is National Centers for Environmental Prediction. There's the ozone sensors. And then there's lookup tables and pre-computed coefficients for aerosol models, for Rayleigh stuff, for Rayleigh optical thickness, ozone, NO2. Of course, the IOPs of pure seawater are all known. You have tables of these bidirectional reflectance distribution corrections, the F over Q. So anyway, all of this stuff is sitting out there with enormous amounts of computer time, having gone into computing these lookup tables, and then having, when you do this pixel, have to go look somewhere and get the ozone, go look somewhere else, get the sea level pressure, and so on. So it's really amazing. And here's the typical, you know, this is something like a 20-year time series of global chlorophylls. This is out of MODIS, I think it was, and including both the land, what's called non-NDVI, non-something vegetation index. So anyway, that's just, to me, a mind-boggling time series that you can generate that. It could have not happened at all. I'll go on to the next view graph. Way back in the 70s, when a few people got the bright idea of saying, hey, we can retrieve chlorophyll from space. They actually flew over to airplanes and flew over ships. The ships measured the chlorophyll. The airplanes measured the reflectance at the airplane, and they showed, oh, you can actually get chlorophylls from the airplane measurement. We could also do this from space. So they started pushing this idea of having a satellite do this. Well, of course, anytime you want to spend a few $100 million on a satellite, it has to get reviewed by all sorts of, you know, luminaries. And so Howard Gordon told me one time that in one of the reviews of what was to become the Coastal Zone Color Scanner, that he just calls it an eminent biologist, so he probably had a Nobel Prize or something. He reviewed the proposal and he said, quote, I know of no competent biologist who considers this an important problem. That is measuring chlorophyll in the ocean. Obviously the guy was a terrestrial biologist, or he did, you know, counted butterfly wings or whatever it was. But that was the review, that was the opinion of this eminent biologist Fortunately, NASA had enough sense to ignore this bozo, and, you know, the rest is history. And we have totally revolutionized not just oceanography, but all of Earth science with all of these satellites that all started with the Coastal Zone Color Scanner back when I was a grad student, or actually postdoc.
It was
Okay, so
in biological oceanographers, the lunatic fringe were like Charlie Yen's, like
Yeah.
CBCS.
Yeah.
Biological oceanographers.
yeah,
That would never work.
yeah. And, you know, I once upon a time, there was an entirely different problem. The Navy came to me and said, Kurt, you know, I think you ought to look into this problem. And I looked at it and said, this is absolutely never going to work. You'll never get around the non-uniqueness business. But I'll take your money and prove that to you. Well, it turns out it worked just fine. So I was happy to say I was wrong. And I now understand why I was wrong. And we'll, if I give my final lecture, we'll see what I was wrong about. So yeah, there were some real pioneers there that are, their names are almost forgotten today, but they really pushed this whole business through way back in the early 70s. And all of this is due to those guys. Okay, that's the end of Jeremy's talk. And he seems to think that there's a lot of similarities in the sky and in the patterns of chlorophyll or whatever it is in the water here. And I fully agree with him. So that's it. Yeah.
Certain sensors warn against using surface reflecting data products in high latitude environments. And I was wondering if there's a single term or a grouping of terms that consider that contributes more to the uncertainty in those latitudes, or is it all of them are kind of equally questionable?
Yeah, I'm not sure. We'll have to, not sure I got all the questions with my bad hearing, but all I can say is what you see here is what NASA's doing today. And whether what you just mentioned will improve that or not, we can talk offline. Yeah.
So at high latitudes, the problem is the sun angle is very low. And reviewing, but the sun angle is low, so multiple scattering is really big. The atmosphere correction.
So would you say that's kind of the primary source of the difficulty in atmospheric correcting high latitude?
Mostly it's, well, there's two things, I guess I should mention one other thing, which is sort of obvious. The first thing is sun angles, so that the atmospheric corrections stress is multiple scattering. This other thing is high latitudes, it's cloudy and stuff.
Right.
And there's not that seasonal, there's not that much snow.
Right.
And there is.
And I also remember when I was doing the interviews, it was one of these things that they only do until the wind speeds were less than 10 meters per second or something. I said, well, you know, what do you do if it's more than 10 meters per second? And the answer is, we don't process the pixel because we assume it's stormy. So it must be cloudy. If the one satellite says the wind speed's 20 meters per second, you can figure you're in the middle of a big storm and you're not going to see the ocean anyway, so don't worry about it.
Which is so not true,
Okay,
because you can be at sea, with really high winds and beautiful sky.
well, that's true, but their assumption was if the wind was too high, it was probably stormy and cloudy and you weren't seeing the ocean, whichever one of these was. Something or something. Okay, that's Jeremy's talk. Hopefully he'll be back in the office next week and you can ask him more questions after you go through and read the report and look at all the equations and ask him about those. Yeah,
I just have a question about the BRDF.
yeah.
Do you have any idea how much error is introduced if you use the BRDF made for case 1 waters on a case 2 water?
It can be pretty big, I guess, because the, you know, the phase functions for like small open ocean particles, low chlorophyll or whatever, they can be a lot different than the phase functions you would get, let's say if there's a lot of mineral particles in the water, because the mineral particles tend to be small, high index of refraction particles. They may have backscatter fractions of like 3 or 4%, whereas phytoplankton are low index of refraction particles And a typical phytoplankton backscatter fraction is like 0.5% or 1%. So you do get some pretty big factors there, but I'm just pulling that out of the air since I haven't actually like done computed BRDF corrections for case 2 waters with lots of minerals and so forth. And that just all gets to be a whole another level of complication that a lot of people, you know, will look at individually for their little area, and they're going to say, well, I'm off the Mississippi River, or I'm looking at the Amazon or whatever. And so they kind of know what's in the water, and they can go cook up their own BRDF correction for those waters and apply to their one little area. And people do that sort of thing all the time, but it's not something that NASA routinely does. Okay, that's it. I'm ready to sit now. And it's 10:25, so the usual hour and a half of torture. But, you know, you guys have now endured the worst. 4 lectures from me in 1 week. Next week, I only have like 2 or something, I think. So it won't be too hard on you.
What do you want?
Your problems next week will be seasickness rather than being sick of listening to me.
So what do you want? 25 after?
Yeah. Okay.
Next month. Lots of pictures.